Computers are often thought of as magical machines that turn electricity into knowledge and are infinitely smarter than you or I could ever dream to be. Well, actually, that's kinda true. Not the infinitely smarter part, but the fact that computers and electronics in general transform mostly invisible energy into calculations, instructions, and ultimately work. Well, it's not magic really, it's physics. And while you may or may not understand it to the point where we can just make a 2080 Ti in our garage, the basic concepts behind electronic computing actually aren't all that difficult to understand when broken down into their different components. Now, before we dive into this, please understand that I am by no means a fully qualified electrical or computer engineer, but I'm currently working on my bachelor's degree in computer engineering at Purdue University. In fact, the main reason I'm working on this video is to help me understand my physics and CS work, so please bear with me if I'm not going super in-depth on concepts. These are just supposed to be the basics. So let's start talking about computers. Okay, so the first thing we should cover is the way in which a computer thinks. The most basic form of information that a computer works with, which makes up instructions, is the bit. Now, a bit is kind of a weird concept to wrap your head around, but in short, a bit is either a 1 or a 0 that's stored in the computer's memory. When translated into hardware terms, a 1 means that electricity is flowing through the circuit, and a 0 means that electricity is not. This is why binary code is made up of 1s and 0s, and it's essentially Boolean operators in a certain sequence that translates to a certain electrical flow path in the circuits of the system. To visualize this as an example, we could have the following byte of information, which is just 8 bits. 10, 10, 10, 10. 1s meaning that there is current and 0 meaning that there is not. So if we were to break this down into a Boolean statement, it would read as follows: true, false, true, false, true, false, true, false. And if we were to actually look at the bus inside the computer, then only the first, third, fifth, and seventh lines would actually have current, even though the full 8-bit wide bus is transmitting an entire byte of information. Now, in a real-world chip, this bus is generally at least 64 bits wide in an x86 64-bit chip, which makes these chips able to transmit larger datasets and improve efficiency per cycle, but it's incredibly more complex. However, when it comes down to it, the bus inside the chip doesn't actually do any data processing. That's all done by the transistors. Now, when you hear about the manufacturing size of a chip, 7 nanometer in Ryzen 3rd Gen for example, they're actually talking about the size of the wires printed in the silicon, and to a lesser, more complicated extent, also the size of the gates of the transistors in the chip. Now, tying this back into 1s and 0s, a transistor operates sort of like a gate. It's more complicated than this, but at a fundamental level, when the base of a PNP transistor has voltage applied to it, it then allows current, and subsequently voltage, to flow through from the collector to the emitter. This basic physical property of the transistor and silicon in general is ultimately why computers are binary systems, and when you really think about it, just super complex I/O machines. When you pair and connect certain transistors up with each other, you then get logic gates. And even though there's only 7 main types and a finite amount of instructions, when you combine these gates into massive arrays and circuits, you can quote-unquote trick the hardware into thinking through your instruction set. Examples of instructions include multiply, add, subtract, divide, modulus, read, write, and the list goes on. But at a fundamental level, computer programming is just stringing these instructions together to get a desired response from the hardware. It's literally putting 1s and 0s in a very specific order to get the outcome. And whether it's the new Call of Duty game or your first Hello World program, the thing that unites all electronic processing is the fact that it all boils down to 1 or 0. On or off, yes or no. With current silicon and binary systems, there's only one answer based on the instructions. However, moving into the future and taking a look at quantum computing, things are changing very quickly and into a type of computing where probabilities are calculated and then run through from there. It's very different than a traditional computing approach, but the basics are all the same. However, moving from a microscopic view of the silicon in your system and into a macroscopic one, there's more to a computer than just processing 1s and 0s. There are several other main systems whose primary purpose is to support the chips with data processing. The most important of these is the memory and storage pipeline. and this is what stores outputs from your system and serves as a cache for future instructions and files to be processed by your chips. When we take a look at RAM, or random access memory, this is meant to serve as a middle ground between your long-term storage, either an SSD or an HDD, and your CPU's volatile cache. And since your GPU and CPU only have at most a few megs of cache on board, RAM is usually much larger in capacity. However, it is significantly slower. Now, taking a look at an actual DRAM chiplet, and heavily oversimplifying, all RAM is a large 3D array of capacitors blocked off into bytes. Your CPU or GPU can then load instructions from these bytes and then read or write to them. Now, this is an incredibly oversimplified look into your system's volatile memory. However, if you want to learn more about computer memory, then we have a video that you can watch in the upper right hand corner. We'd really recommend it if you're at all interested in the history of computer hardware or are just like me and like geeking out on the weekend. But I digress. When taking a look at a computer system from above and breaking it down into each of its individual components, each and every one is interconnected and designed to perform either some highly specialized task, like your motherboard's chipset, or stand by as a general purpose decoder, like your CPU or GPU. But at the end of the day, all computers are just bundles of wires, transistors, capacitors, and other electronic components that are assembled in a very specific way to allow for an inanimate object to virtually understand the user, as long as you're speaking through some sort of programming language, or better yet, assembly. Thank you so much for sticking around until the end of this video. We really do appreciate your support and wanted to save a few things until the end. Firstly, I've been on a hiatus of sorts, and it's been a hot second since we've spoken. And while I generally don't like making excuses, the main reason for my absence from the platform is because of university. Plain and simple. Like I mentioned earlier in the video, I'm attending Purdue University and I'm currently working on my bachelor's degree in computer engineering. While yes, my schoolwork has been taking up a ton of time, I've also been trying to experiment with different content styles. Sitting on my workstation right now are several unreleased videos that are more experimental with hardware and have a more silly and informal tone to them. If you're at all interested in seeing these videos release, then tell us in the comments and we'll finish them up and make them look somewhat presentable on the channel. But in the meantime, I'd like to thank you once again for sticking through the whole video, and if you enjoyed, consider leaving a like and subscribe for more tech-related content each and every week. Thanks again for watching, and I'll catch you in the next video. Bro, it's Louisville, Kentucky.
It's not Louisville.
It's Louisville, Kentucky.
It's Louisville.
Jesus Christ. Okay. That's going in. I was recording that whole time.
I know, I saw your computer. It's Louisville.
Okay. Well, I'm gonna start recording.